Okay, good morning, everybody, and welcome for the last lecture in this course on the automated experiment. So throughout the previous 6 lectures, we went pretty at depth at the concepts such as Gaussian processes, Bayesian optimization, and so by now, if you follow the community, Bayesian optimization is starting to be exceptionally popular. So the number of papers where it is used is probably increases by multiple factors every year now. So we talked about less conventional, but also available now areas such as structured Gaussian processes and the Bayesian inference. And over the last lectures, we talked about the variational autoencoders as the way to introduce the latent variable concepts, and deep kernel learning as the way to run the Bayesian optimization over very high dimensional spaces. So normal GP and BO by now is the bedrock of the field. There are many companies and groups that are using it. Going beyond simple Gaussian process into the structured GP DKL is probably fairly unusual, even though it started to get adopted very, very fast. So today we are going to talk about the look at again at some of this concept, but most importantly, we are going to talk about a very unusual concept, or in some sense, for physicists, it is very natural concept. We just take it for a given, which is the causality or relationship between the variables, and the ways how we can integrate multiple optimization loops. So both aspects are important. So let's look at them and see how they work. So as I mentioned, now the classical Bayesian optimization is already become a standard in the field. So 3 or 4 years ago, there was relatively small number of groups that worked on it. Now this is something that is a part of the active learning in experiment, in multiple theoretical domains, and so on and so forth. So general concept of the Bayesian optimization is that we start with defining our parameter space. So this parameter space can be a concentration space of the system. It can be parameter space of the growth. It can be something else. But the important thing is that we know what is our playground. So we synthesize and do measurements of some functionality over this parameter space. So from the point of view of Bayesian optimization, synthesis and measurement is the same thing. We just need to find a way to identify quantitatively the functionality that we're interested in. By necessity, we can do this type of measurements only in the small number of points because experiment is expensive. And the value proposition from the Bayesian optimization is that it allows us to do it more effectively than just exploring everything by the grid search. So once we've done the measurements, we identify our surrogate model. So notice that the important thing is that if we measure spectra, we cannot define the surrogate model based on spectra. We need to identify what is that we care about the spectra. So it can be the position of the peak, for example, indicative of our band gap. It can be width of the peak. So the narrow peak means that material is stable. 2 peaks may mean that material falls apart. It can be the amplitude, which is PL intensity. So in other words, we need to identify what is that we want to optimize. The surrogate model gives us the prediction and uncertainty of the parameter that we are interested in over the parameter space. So this is what the Gaussian process or structured Gaussian process can do. And then we build the acquisition function, which is essentially defines how we want to balance the prediction and uncertainty. So how much risk we want to get versus how much, what do we want to accomplish. So if the acquisition function is exploratory, that means that we want to understand the behavior of our parameter, our measurable parameter over the parameter space. So we don't care about specific outcome, we just want to understand. If our acquisition function is greedy, that means that we want to find either minimum or maximum. And practically, we try to balance the exploration and exploitation. So we do it through the acquisition function. Acquisition function somehow combines the prediction and uncertainty, and the way that it's up to us to decide how. And then the maximum of the acquisition function defines the point where we are going to take the next measurement. And then we are going to repeat this process as long as we run out of the experimental budget. And of course, how greedy to make the acquisition function depends on the context. So if we have a long exploration campaign ahead of us, it makes sense to start with being exploratory. If we have the very few experiments, it makes sense to be greedy. And another very important thing is the domain knowledge, because ultimately we very often can fine-tune hyperparameters on the similar problem, but it really will help us a lot to know how many maxima we expect. So if we expect multiple maxima of the function we want to discover, we will choose one set of policies. If we expect that there is only one maximum, then we develop different set of policies. So the domain knowledge is implicitly very important. We can incorporate it through the structured Gaussian process, then it makes it more solid. But even when we do the hyperparameter optimization in the classical GP, we implicitly use it. So we discussed in detail the roles of the noise priors, because these are super important and they can be interpreted differently. So the noise priors for classical Bayesian optimization person is the hyperparameter. The noise prior for the experimentalist is the behavior of the tool. So these are kind of important consideration. This being said, this is by now a well-established approach. Not for a long time, it may be last several years, but by now, general knowledge how to realize these loops are here, and that's why we discussed it in detail in the first several lectures. The problem is that this is absolutely not enough for the real-world workflows that incorporate multiple moving parts and multiple decisions. So very often, if we work even with the same material systems, we need to make decisions when we balance the multiple source of information. For example, we can use the stability of the combinatorial libraries and use them as the predictors for the properties of the thin films. The thing is that the microcrystals are cheap to explore. Films are much more expensive and take much more time. The problem is that we don't expect that the properties of the crystals and the properties of the thin films are exactly the same. So we need to somehow balance the knowledge, or balance the knowledge in what we learn developing the combinatorial libraries with our belief how much does the information learned for optimization of microcrystals, how well can it predict what happens with the films. So this type of problems is something that we encounter in the lab every day. So there is nothing unusual about it. We do not have a very well-established frameworks for that. And so multi-fidelity methods is one way to get it done. So second part is that if we have multiple characterization tools, sometimes the question is, can we learn more by running this type of experiments jointly rather than separately? So that's something that we are going to look at today. So we briefly, over the last lecture, we briefly introduced the concepts that are necessary to at least start building the nonlinear workflow. So we talked about the multi-objective Bayesian optimization. So if we have more than one target function that we care about, and we want to optimize our exploration cycle so that we learn about several functionalities at the same time. So if you will, that means that we have one optimization cycle with the multiple targets. And then we also talked about the multi-fidelity and multitask Gaussian processes. So the several topics that we are going to talk about today is the workflows with the multidimensional data. So what are we going to do if instead of one function or several scalar functions that can be used as an objective, what can we do if we have we can observe only multidimensional data like images or spectra? And briefly talk about what are the possible solutions for the co-orchestration of multiple research tool and co-navigation of theory and experiment. So the reason why we need all those is, as I mentioned, because for multi-target, we need to multi-objective optimization. Very often we have specific industrial tasks like battery testing. There are multiple parameters that we care about. For decision making, very often we make decisions based on the multiple sources of information. So we don't necessarily rely on the exploration of the single parameter spaces. Sometimes we learn about the same object from multiple sources of information. And we talked about two strategies or two tools that are now out there that allow us to approach solving these complex tasks. One is the multi-fidelity Gaussian process. So the classical setting for that is that and as I mentioned, multi-fidelity and multitask can have two meanings. One is the name of the mathematical algorithm. Another is the sort of problem that we are using it for. So strictly speaking, we can use a multi-fidelity Gaussian process to solve the multitask problem and multitask Gaussian process to solve the multi-fidelity problem. But the important difference is on the side of the mathematics, how it is realized internally. So the typical example for multi-fidelity Gaussian process is that we have easy to evaluate function and expensive to evaluate function. So the easy function is considered to be the proxy for the expensive one, meaning that there is some correlated relationship between two of them. And then our task is to learn the expensive function using the cheap function. So in this process, we learn three things. We learn the kernels and parameters for the cheap function and for the functions. So they have the common kernel in the parameter space. And we learn the correlation kernel that says the relationship between the expensive and cheap functionality. So the important thing is that once we run this experiment, we learn both the parameters of the Gaussian process and the relationship between the two. So the policy or the acquisition function should balance the evaluation costs. So if the high fidelity function is cheap, then we can just measure the high fidelity function. Realistically, a high fidelity function is expensive, low fidelity function is cheap. So we need to balance our experimental budget. When do we measure the expensive function? When do we measure the cheap function? So that's relatively simplistic model. It works. It is very effective in certain cases, but ultimately it is not super complicated. So the multitask Gaussian process is a totally different thing. So the version that I've shown you is based on a so-called linear co-reorganization model. So basically what it means is that we have a very deep concept of having the latent Gaussian processes. Same type of latent variables as we had in variational autoencoders. But so latent variable is essentially unknown cause. What the multitask Gaussian process does, it's we define the number of these latent processes. We can say that there is one, there are two, there may be three. So it's up to us to define how many we want to have. Latent processes themselves are not observable. So we just know about them based on the observation of tasks. So what happens is that we assume that each task is formed as the sum matrix operation with this latent variable. Since the easiest way to represent it is that if we have three latent processes, then our task is simply a 3x3 matrix multiplied by the value of these latent processes. So when the multitask Gaussian process learns, is that it tries to reconstruct these latent variables, and it also tries to learn the matrix that connects the latent variables and the observed task. So it's a fairly complex and abstract mechanism, and it takes quite a lot of time to figure out how it works and how to operate it. But practically, it solves the problem of having some underlying physical truth that we don't know, and then we try to do different measurements at different locations to learn both the underlying model and the observational model that relates these underlying parameters with what we can actually do. So this is a very powerful tool, and we're just starting to use it to the full effect, but it allows us to branch our discovery workflows in the Gaussian process, in the Bayesian optimization. And of course, in the real world, the problems can be even more complicated, because imagine that I studied the combinatorial library. So in this case, so kind of what are the latent variables? And the answer is that the latent variables is something that relates to the physics of the material. In the most simple case, I can say that the latent variable is the composition-dependent polarization. So I know that in the combinatorial library, the composition changes across the sample. I know that polarization should change with the composition, so I can say that my latent variable is just the polarization. Practically, a situation is going to be more complicated because different compositions have different behavior when we try to deposit the material. So, for example, the temperature of Curie temperature can change. So in the one half of the library, Curie temperature can be above the deposition temperature, so the material grows in the ferroelectric state. The other part of the library, the Curie temperature can be below, so the material grows in the paraelectric state, and then when we cool the sample, it undergoes the transition. So if this happens, the surface topography of the film would be very different. Secondly, if you have a strongly doped material, then simply the growth can be different. So we can have a step flow growth here, and we have the island growth here. It's also entirely possible, which basically means that the latent factors that determine the evolution of our measurable properties can be considerably more complex than just polarization dependence on concentration. It can be parameters developed dependent on the growth condition, parameters dependent on the misfit strain, and so on and so forth. Second problem is that our observation is, strictly speaking, not polarization itself. We can observe the hysteresis slopes, we can observe the surface topographies, we can observe the micro-Raman spectra. So it's not a single variable like we say the maximum of the peak. It can be something fairly complicated. And in order for us to use the Bayesian optimization, we need to find a way to represent this type of data through the physically relevant parameters. This can be done using simply the physics-based representation. So we can say that we want to explore combinatorial library based on roughness, or we can introduce the index function that says the film is rough or not rough. But then the problem of the feature engineering comes front and center, simply because we need to find a way to define what is that we are exploring. So notice that, strictly speaking, it is possible, instead of the multitask Gaussian process, instead of using the linear matrix that connects the latent variable to observations, it's possible to use something like a decoder architecture. So something like decoder part operational autoencoder. This is a possible strategy. I am not aware about anyone having realized it at this point, so I wouldn't be surprised that it would be done in the next year or two. But for the time being, the fact that it's possible to do it this way doesn't mean that it has been done. And if it has not been done, we simply don't know what are the opportunities limitation of this model. Nonetheless, going back to the combinatorial library, it brings us to several scenarios about how we can study this type of systems using multiple methods. So in these cases, everything depends on how do we want to run the process, discovery process. So easiest example would be if we just measure sample on the grid by multiple measurements, and then we can find ways to simply correlate different observables. In other scenarios is when we want to use the active learning. So in the active learning is dependent on the low dimensional data, or we have a good scalarizer for our data, then this is something that can be done by Gaussian process or structured Gaussian process or something like that. If it is based on the images and spectra, we don't have a way to do that. So I will show you how it can be hacked, but for the time being, we don't have the mathematical framework that we can trust to do that. So we can have active learning when we have full low dimensionality proxy data of one functionality and active learning for another functionality. This is multi-fidelity Gaussian process or structured Gaussian process. So we sometimes need so problem is that very often our experimental problems are much more challenging than that. So we'll have the need for active learning when we have high dimensional proxy data and use it for active learning for another high dimensional data. So for example, we want to use the results of the topographic imaging or PS response imaging to select locations for the electron microscopy. So from mathematical point of view, this is a very complex part. From point of view of experiment, this is our everyday reality in physics lab. And even worse problem is what if we have two active learning methods? So we can study the sample by different imaging techniques. We need to, so let's say we have two types of electron microscopy. So how are we going to select locations for one measurement and choose whether we should take the measurement here by one modality or measurement here by another modality? So from mathematical viewpoint, these are super complex. From the physics point of view, these are absolutely normal. These are the decisions we need to make every day in the lab. So I'll show you some of the beginning thoughts about how we can approach this problem. But before we go there, let me spend another maybe another hour or so talking about a very important aspect of the physics and material science research, which we typically take for granted, but actually we shouldn't. And this aspect relates to the correlation and causation. So notice that I have highlighted multiple times that if we have the multi-fidelity Gaussian process or multitask Gaussian process, we assume that there is a correlative relationship between the two functions, or there is a same mechanism by which the observations are emitted from the latent variable. And the important thing is that these mechanisms are symmetric. In other words, we assume that the low fidelity observation affects the high fidelity observation same way as high fidelity affect low fidelity. We assume that the coupling between the latent variables that give rise to observed tasks is also symmetric, so there is no difference. We need to know that in the real world, there is a big difference between the correlation and causation. So let me show you a few examples. So we are not going to go in this any detail. I'm just, there is actually very little work being done now in the space of the causal machine learning and materials. However, there are already companies like a Causal Length, which basically offer the AI solutions for the industry based on the use of the causal ML. In other areas, situation is totally different. So the causal machine learning method is probably one of the most rapidly growing area now. If you paid attention, a few years ago, the Nobel Prize for Economics was given by Imbens and Rubin. So their accomplishment is introduction of the causal methods in the economic research. So in areas like medicine, economy, social fairness, and I'll show you why, causal methods are now developing very, very, very fast. In material science and physical sciences, we just starting to essentially scratch the surface of this process, but let me explain what it is, why is it important, and how it relates to the Gaussian processes. So let me start with a few examples. So these are the two graphs. One graph is the computer science doctorates awarded in US in the years from 2000 to 2009. This is the total revenue generated by the arcade games. And you can see that the correlation is exceptionally good. Does it mean that there is a causal mechanism that connects them? So is there some relationship between these observations? The answer is, yeah, we can speculate that the people who go in the arcades and play computer games, they grow up to be geeks and get their computer science doctorates. It doesn't kind of, if we look at the data a little bit more carefully, maybe it's not so good a comparison because these are done at the same year. If these were shifted by 10 years, that would be reasonable. If it is same year, then maybe not. But let's look at another example. So this is the non-commercial space launches versus sociology doctorates. Again, correlation is actually pretty good. But in this case, it would be very difficult to come up with the plausible mechanism why these two would be related. So, and then we can kind of come up with the more extreme cases. For example, the correlation between the sales of the Japanese passenger cars and suicides by the motor vehicles. So, I mean, they are clearly correlated, but I wouldn't speculate about why this might be the case. And the same thing about, okay, winning more than national bee versus number of people killed by venomous spiders. So the point is that these examples clearly show that correlation is not causation. Very often we can have observations which are strongly correlated, and the degree to which they are correlated doesn't tell us much about the causative mechanism between the two. So another example. So if we kind of look at the statistics data, there would be a correlation between the, let's say, consumption of ice creams and drowning. So the question is there a causal mechanism between the two? Probably not. However, we can speculate there can be some hidden factors that actually affect both the ice cream consumption and the drowning, and this hidden common factor is actually the temperature. So when the temperature is high, people buy more ice cream. When the temperature is high, people spend more time in the water. When people spend more time in the water, accidents happen more often. So notice that once we start to think about this elementary example, we can have correlations which are induced by much more complex causative mechanism than just direct cause and effect relationship. Why does it matter? It matters because I'm showing the examples for the fairly abstract concept, for fairly kind of life-related concepts, not materials, but exactly the same logic can be applied for material synthesis. So for example, if I'm exploring my combinatorial library based on the surface topography, on the first approximation, I can assume that my surface topography have nothing to do from the ferroelectric properties, unless I assume that both topography and ferroelectric properties have the common origin. So if I'm able to identify this common origin, I can determine the degree of the relationship between the two, and more importantly, I can figure out how to control them. Second problem is that not having access to this common origin can simply cause me to make the incorrect conclusions about what matters, and making incorrect conclusion means that I cannot adjust my exploratory pathway or my industrial process well. So let's look at a few examples. And again, I'm going to show you the examples of how it is done in medical or fields or in economy. And the reason I'm doing it is because this field, there are simply not examples of this being done well and comprehensively in materials for the time being. But it will be because the problems that we face are exactly the same one as appear in these more developed fields. So what is the basic principle here? So one of the key things that people care about in medicine is so-called treatment effect. So treatment effect is very easy to understand. So imagine that you have a headache, you want to take a pill, and then your headache disappears. So the doctor may ask a question, what is the treatment effect of this pill on this person? And it's defined as very simply. So what is the outcome if I receive the treatment minus the outcome if I have not received the treatment? So it's very convenient to think about it as the probability that the pill will help me with the headache. And this concept of the treatment effect would be absolutely common across other fields. So it's the same concept as for marketing. So if this person saw the ad or not, how more likely is this person to buy the product? It is common in medicine and common in materials. If I synthesize this sample differently, or if I apply this step during the synthesis, how would the outcome be different? But you see, the key problem here, and there is a reason why this framework has been first developed in medicine, is that if we talk about people, we really cannot imagine the situation that the same person is both treated and not treated. It's impossible. So how is it solved in medicine? Very simple. We choose the group of roughly the same people, and we just look at the we give half of them the treatment. We don't give the other half of them, don't give the treatment to the other half of them. We compare the results. But in this case, the key thing becomes that the groups have to be comparable. So whatever that means, because if we give a different treatment to different groups, it's not going to work. And I'll show you the example of the things called Simpson paradox that appears from that emerge as a result of this mismatch. In physics and material science, we don't have to deal with this type of problem on the simple level, because in material science, nothing precludes us from having 10 samples and try to treat some of them and not others. And therefore, we kind of can compare the samples under same sample under different condition. So we utilize the fact that we can run the experiment and we can run it in repeated fashion. However, this is only superficial, because there are many cases where we cannot do experiments even in material science. So let's look at some of the examples of what problems can appear in this context, and then try to connect it to the material science throughout the discussion. So what's the problem? What type of problems can appear in the concept of the treatment effects? So let's look at the picture from Julia Pearl presentation. So Pearl was actually a professor of physics and long time ago and worked in the field of the superconductors. Then he switched to the understanding of the causal mechanism, and for the last 40 years he has been working on figuring out the mechanism of the causal phenomena. So basically he is the Turing Prize winner, so it's roughly the same thing as the Nobel Prize but for computing. And essentially there are two big schools of the causal thought. One is the Rubens Imbin, the economic Nobel laureate guys. The other is Perlin. So let's look at the examples when it is important. So imagine that I show you this graph that shows you the cholesterol and exercise. And what you're going to see here is a little bit uncomfortable. So this is a statistics that shows that the more you exercise, the higher is the cholesterol, right? At the same time, if you go to the doctor will typically tell you that, you know what, your cholesterol is high, you should exercise. So what's going on? And the answer is that if we take exactly the same data set, but stratify it based on the age, what we are going to see is that within each age group, the more you exercise, the lower is your cholesterol. However, the higher is the age group, you see what is the origin of this trend. So it is very clear that the higher is the age group, the more people exercise. So that's why we have this trend. And the confluence of this factor, age, and the effect of the cholesterol and exercise reverses the effect. Why does it matter? It matters because if we have the same data, we can come to the totally different conclusions about whether exercise is good for cholesterol or not. If we look at the data in this representation, we conclude that the exercise increases cholesterol, which is not good. And if we look at the data in this representation, we can clearly see that exercise actually reduces the cholesterol. We just need to deal with the trend that elder people try to reduce cholesterol and therefore they exercise more, but this is not enough. So in other words, without exercise, the dependence of the cholesterol on age would be much higher. As it is, it's slower, but we don't see that because we see only the cholesterol and exercise level. The reason why it matters is that because in this particular example, we have a very simple system. Our data is two-dimensional, it's just X and Y, and we have a simple and natural way to stratify our data points. In many other cases, the data is high-dimensional, the factors that allow us to stratify it, like age, are not immediately observable. And this can be one factory, this can be another factory. One factory can be in Texas, another factory can be in Florida. So there is a difference in humidity. Both of them try to reduce the humidity to improve the effect, but the natural humidity in Florida is much higher. As the result, total effect can be opposite. So it's very easy to make fundamental errors in the interpreting the data and therefore selecting actions if the causal structure is not understood. It can be very bad in other examples. So this is another example of the Simpson paradox in the medicine. So imagine that we have the drug A and drug B, and we try to figure out whether this drug will induce the blood clots. So as you can see that drug A produces the blood clot in larger number of cases. So seems like if you talk to your doctor and he has to figure out which prescription give you, looks like that the A is definitely better. Now let's look at the same type of data, which is stratified based on gender. And lo and behold, I mean, you can check the numbers, but lo and behold, it looks like drug A is actually worse because it causes the blood clot more often. But if you stratify it based on the males and females, you can see that actually for both of them, the drug B is actually worse. So it turns out that if we try to make a prescription for female, we should choose A. If we try to make a prescription for male, we should choose A. But if we make a prescription for the populace made of males and females, we actually should choose B. So again, this is an example of the Simpson paradox. And the origins of this inversion are not necessarily obvious. So there is a reason why the doctor tends to prescribe one of these drugs more often to male rather than female. There is some hidden mechanism. But third example where it becomes super important is obviously everything related to the social issues. So for example, in 70s, so 50 years ago, UC Berkeley was sued for gender discrimination. And the assumption was that out of 8,500 male applicants, 44% were admitted, but out of 4,300 female applicants, only 35% were admitted. So a clear case of the system bias towards the males. But if you start to look at the individual departments, you can see that the statistics is in fact heavily tilted towards the females admission. So for example, for males in the department A, there are 62% of male, 82% of female, 63, 68, 37, 34, 33, 35. So basically, the more females are admitted than the males. So what's going on? The way the paradox appears because the women disproportionately apply to the departments with the low acceptance rates. So, and while male disproportionately apply to the departments with the higher acceptance rates. And that skewed the statistics in such a way that things are fine department by the department, but things are not fine overall. So I'm showing this example because it illustrates that Simpson paradox can appear in multiple settings. Once it appears, it can usually create considerable, very kind of thorny issues related to the social justice and so on and so forth. And these are important issues to address. A lot of people are working on that. But the important thing is that the same type of problems appear in the context of the material science, because very often we make decisions based on what is easier to do as opposed to what is the right thing to do. So it's important to balance this type of things. So the question becomes, how do we accomplish this problem? Is there a systematic solution? And the answer is that at the level of data analysis, the solutions exist. It's a very special area of science, and it will require considerable time investment to learn how to approach it. And it will require some amount of time to actually adapt it for your specific domain. But if you have the data, so if you run the lab or manufacturing organization or product line or whatever, you would be able to do that. Combining this with the active learning is the new area. People who work on it most are now in the context of the ad placement or medicine and so on. However, they create the frameworks that allow us to do roughly the same things. But before, so obviously there is no way we can go through it at one lecture. That's maybe more like a full semester in university, and I'm not sure who can teach it well at this point. It's new field, but there is some basic terminology that would be useful to know and understand, because if you know and understand it, then you would be able to ask questions and sort of think about the causal issues throughout the process. So the basic setting of the problem is the same as so let's look again at our case of temperature, ice cream consumption, and accidents. So observations give us correlation between these parameters. What we'll want to learn is the causal link. The reason why we need to learn the causal link, because we ultimately want to reduce the number of accidents. And supposedly if ice cream consumption and accidents are related, the natural question is, can we reduce the number of accidents if we sell less ice cream? I mean, it's not a very wise statement. Obviously, we cannot. But that's the idea, is that in this case, we know the cause. The question is, can we use this method when the cause is unknown? The best way to learn the causal structure is to run the experiment. Obviously, we cannot always run an experiment. First of all, in this case, it would be simply not ethical. Secondly, sometimes experiments are simply too expensive or take too long. So what can we do? So the basic framework to deal with the causal questions is a so-called causal graph. So causal graph is basically what it is. So imagine that we have phenomenon A that causes phenomenon B that causes phenomenon C. Or phenomenon A can cause the phenomenon C directly. So basically, causal graph is our phenomena. The difference between the causal graph and everything else is that the relationship is always one directional. So A causes B, but not B causes A. This is very, very different from how we use the normal physical notation. So in physics, we say that, let's say we have a universal gas law that says PV is equal to RT. In this case, both sides of the equations are equivalent. It's just a relation, it's just the equality. So we can switch them without changing the meaning. PV is equal to RT, and RT is equal to PV, so it doesn't matter. It is very convenient, but this is the case where we are kind of hostages to the mathematical notation that we learned in school, because the mathematical equality represents the equal relationship, which goes both directions. Causal relationship go only in one direction. And the causal community have developed this assignment operator or Walrus operator, which shows the directional relationship between the variables. So in this case, we say that A is caused by some exogenous factor or noise, if you will, U naught. B is caused by U1 and A. C is caused by U2, B, and A. So if we change B, we will change C. If we change A, we will change B and we change C. If we change C, we are not going to affect either B or A. In physics, we take this relationship for granted. We don't even think about it. So it's our intuition. This intuition works exceptionally well for simple systems when the causation effects are obvious. It works exceptionally well when we can run the experiments. So if we run an experiment and change B and C changes, but A does not, then the causal effect goes from B to C, but not from B to A. The problem is that this simple logic fails if we go beyond simple experiments or small number of observables. If we observe multiple aspects of the material behavior in the same time, we don't necessarily know which one causes another one. For example, imagine that you make a ceramic. So the ceramic sample has certain color and certain conductivity. So color is very easy to measure because we just see it when we take it out of the furnace. Conductivity requires physical measurement. So can we say that there is a correlation between the color and the conductivity? Can we use one as the proxy for another? And if we could, then we would be able to use the multi-fidelity Gaussian processes where we optimize for color because color is the proxy signal for conductivity. The problem is that color depends not only on conductivity through the free electron concentration, but it can depend on other effects. So there is a causal link between color and conductivity, which is carrier concentration, but the color depends on other things. For example, if we have a little bit of contaminant in our system or the surface become rough or something like that, that's another mechanism. And surface roughening does not affect conductivity, but it affects color, which basically means that if we try to use any complex, meaning more complex than the simple Gaussian process approaches to optimize the material, we need to understand the causal relationship between the parameters that we can measure and parameters that we care about. And in order to do that, we need to somehow build this causal mechanism based on whatever information is available for us. Most of the time, we do it based on the domain expertise. But sometimes we cannot do it based on the domain expertise, and this is the point where we need to discover things. So this being said, what are other things that we need to know? So a very important concept that appears in the context of the causal machine learning is the word intervention. So what is intervention? So there are two things which at the first glance are very similar, but fundamentally very different: conditioning and intervention. So conditioning is what is the probability of x being x if y is equal to y. So conditioning only modifies our view of the data. Intervention is what is the probability of y being certain value if we force x being something else. So in this case, we actively set the value variable to a fixed value. So it's like running the experiment. So the intervention changes the system. Conditioning does not change the system. So physical experiment is intervention. Analysis of data sometimes allows us to predict what the intervention would do, but most of the time does not. So the purpose of the causal discovery is, can we predict the effect of the interventions if we have access to the data only? So interestingly enough, the whole logic of this causal discovery is such that there are parts of it which are, for physicists or generally for material scientists, are super easy and natural, and reversely, they would be complex for the person doing the statistics. And there are aspects of it which are very complicated for physicists, but sort of natural for the person doing statistics. So that's kind of a little bit being in the wonderland. But let's look at the basic property of the do operator. So it essentially, if I do the do operator on B, then basically means that I break any connection between the A and B or U1 and B, and I simply tune the B directly. So I make an experiment here. It is possible in some cases. It is obviously not possible in other cases. So the second thing that is important to know is what is called the ladder of causation that is invented by, again, Judy Pearl. So the first level of the ladder of causation is so-called association, or finding the correlative relationships. So all machine learning, including Gaussian process, structured Gaussian processes, what's not, except for causal ML, if it is said specifically, is exploring the associative or correlative relationships. So we just look at the data, we find the correlations within the data. So the things that we want to do in the real world are intervention. So intervention is what will happen if I come up with some abstract scenario. So if I take aspirin, would my headache be gone? So generally, we are asking hypothetical questions because sometimes it's better to be able to find the answer to the question rather than run the experiment. And sometimes we want to answer these questions based on the prior data without doing the experiment directly. So this is intervention. Sometimes we can ask these interventional questions based on the data, purely correlative data. Sometimes we cannot. So the role of the causal methods is basically giving a systematic framework that says in these cases, having access to data allows us to ask the answer interventional question, and in those cases it cannot. So the third level is the counterfactual, which is essentially understanding the fundamental mechanism beyond the process. So what if what would have happened if I have done things differently? So what would have happened if I started the experiment under different conditions? What would have been an outcome? In physics, either intervention or counterfactual questions can be answered if we know the physical mechanism or model. It's very easy to do that if we have the model for behavior. In the statistics world, this cannot be answered. So the counterfactual questions can be answered only if we have the physical model of the process. So the reason why it is important is obviously it's clear, right? So it's much better to invest in the small amount of programming rather than large amount of the experimentation. Counterfactuals is even more complex thing that it's kind of lesson learned type of stuff, and it's very, very difficult to answer those. So knowing the causal relationship between your observational and control variables is super important in order to be able to make decisions in the real world. So imagine that you will look at this Simpson paradox example where we try to define what is the relationship between the cholesterol and the exercise. That's obviously very relevant because our doctor need us to tell us whether we should exercise or not. And it's easy to make the wrong recommendation. So this, of course, applies to pretty much everything we are doing, including the manufacturing, optimization, and so on and so forth. So the way it is done is through the sciences called causal discovery and causal structure learning, which is basically the umbrella terms for the collection of methods that allow us to learn causal structure from observational or interventional data. So important thing is that very often we rely on the expert knowledge here. So expert knowledge is basically the knowledge of the professional that either defines or allows to the disambiguate causal relationship. So this can include everything from randomized control trials, law of physics, human heuristics, and so on and so forth. For all of us, we generally, as the community, do not work with the causal discovery exactly because we are all experts in our respective fields, which means that we rely on our integrated perspective on the laws of physics, heuristic, sometimes controlled experiments, in order to understand the causal structure. And again, for simple problems, it works. For complex problems, maybe not so much. So the idea is, of course, that if we want to use the causal discovery, practically we need to synthesize the causal discovery methods like do, why, whatever with the expert knowledge. And there are algorithms that actually allow us to do that. So we can combine the expert knowledge and the causal discovery tools. Now, what are other things that are good to know? So one thing that's important to know is called the independence phenomena. So basically, independence is very easy to define statistically, that if the probability of two phenomena happening simultaneously is equal to probability of product of their probabilities to occur independently, that means that they're independent. So extension of this concept is so-called conditional independence. So we say that one is X and Y are conditionally independent given Z if that their conditional probabilities are independent. So these fundamental definitions are used in order to establish the nature of the causal graph. So for example, if you have a causal graph, you can say that two nodes are independent if there are no open path that connects them directly or indirectly. And we say that they're conditionally independent given Z if there is the Z that blocks the path that connects and Y. So this is important because that basically tells us how to make the intervention and what is the cause of the what are the causes of the correlations that we can observe experimentally. So going forward, if we have only two effects, then we have either A induces B or B induces A. So there is only two ways they can be related. If we have three observables, the life becomes more complicated. So in this case, we actually have already three possibilities. So one possibility is so-called chain. So A causes B, B causes C. So in this case, we can say that A and C is independent if B is fixed. So they're connected only through B. If we fix the value of B, then C becomes independent on A. The second example is so-called fork. So fork is when we have B, which causes A and C, but there is otherwise no relationship between A and C. They just have a common origin. So this one is also relatively straightforward. So again, in this case, A and C are independent if the B is fixed. So these are very easy to understand logically. You basically can think about how the causality flows either like this or like this. But there is a very subtle third possibility when B depends both on A and C. And that one is something that is the cause of a tremendous amount of the misinterpretation of data in literature, or wrong decisions made, or even wrong understanding of the phenomena. So first of all, let's see what goes on in this case. So imagine that B depends both on A and C. In this case, A and C are independent. There is no causal relationship between them. However, if B ends fixed, then A and C are no longer independent. So there would be some relationship between them. So how comes? So let's look at the very simple example. Imagine that A and C are random variables between 1 and 3. Let's see that B is the sum of these two variables. So now we know that if A and C are independent random variables, that A and C is independent. But if we say that the sum of them is 4, they stop being independent anymore. So there are only the three combinations that can give us 4, which means that even though A and C are conditionally independent, they are not correlated, but they become correlated if we observe C. So in other words, if we have multiple observables and the relationship structure between them is such that we have a collider, if we try to condition our data based on this collider, then we introduce the dependence between these two observables. Does it matter in real life, or is it a very abstract concept? It actually affects the real world big time. The simplest example of this is so-called Bergson paradox. So imagine that you have a company where there is people who work, the two things matter for your success. One is how well you can work as a part of the team. Another is how well can you write a code. Very normal situation. So imagine that someone, sort of leaving aside the kind of obvious personality issues, let's assume that someone notices that in this company, generally people who are better in coding are worse in collaborative skill, and people who are better in teamwork and collaboration are worse in coding. So does it mean that generally the coding skills and collaborative skills are anti-correlated, meaning that naturally if you are better at one, you would be worse in the other? So this is a loaded question. You have to be very careful asking this type of questions, and you have to be very careful answering them for very obvious reasons. However, imagine that you are a CEO of the company. If it's your company, you need people who do both. What are you going to do? And the answer is that let's look at how the hiring process have been done. And if we hire people based on the combination of their coding skills and the capability for teamwork as a sum, we are always going to have this behavior. Because if we assume that in the original population, so this is our total workforce, if we assume that there is no relationship between the coding skills and collaborative skills, just by definition, if we hire people based on the sum of these components, then in our hired team, this would be anti-correlated. It's not that there is any fundamental relationship between coding and teamwork. The answer is that even if there is no relationship, if they are not correlated, if we use the sum of those as the criteria to hire people, then in our workforce, they would be anti-correlated. This is simply the effect of having the collider. So what you are going to do about it, that's a different story. So you can change your hiring practices, you can change your assessment, you can say that this is a natural way how we build the teams, and therefore we will build the internal teams combining this experience. That's a different story. And what policy you make based on this observation is a different story. But there are two things that matter, is that if you make this observation, you cannot make any claims regarding the relationship between the coding and teamwork. That has to be a separate study. And second thing is that what you have is the consequence of the policies that you introduced. And this is another reason why understanding causal mechanisms are super important. And that's also a reason why it is important to kind of understand the mechanism and formulate the policies, but not mix those in the same thing, because otherwise things can go horribly wrong. So this being said, and obviously you can kind of speculate that the number of cases when something like this becomes important in material science or the industrial decision making is of course very significant. So we always make policies about where we invest, how we make the criteria for invest, and we need to be prepared for the real world results of this type of decisions. Now, let's kind of go back to the causal framework and look at the three useful words. So again, we are not going to learn how to use them. We're just going to introduce them that you recognize that that's what you need if you decide to go in this area. So one word is the estimand. So estimand is what we want to know. So it's a kind of something that represents the true value of the parameter. So if we are interested in the average height of adults in specific country, then the actual average height is the estimate. So in other words, that's something that we're interested in discovering, and we assume that this true value exists. So estimate that this is true value. So estimate is the approximation of this true value based on the partial statistics. So estimate would be measuring the height of everybody in the country. So for obvious reason, that's not something that we can do. Estimate as what we can do with given the limited experimental data. So if we measure the height of 1,000 men rather than whole population, then we can get the average height of this 1,000 men, and we assume that the average height of the 1,000 randomly chosen adult men will be a good approximation of the true average height of all men in the country if we measure that. And the final thing that matters is the estimator is basically the rule of formula by which we derive the estimate from the data. So for this example, the estimator is something very simple. It's just the average. So it's kind of trivial. We all know how to calculate the averages for dispersions. And in many cases, we even know how to calculate the p-values. But it's not always simple. So again, the key thing about the causal discovery is that it allows us, given the observational data, to say how we should build the estimator in such a way that our estimate provides us the good idea about the estimate. So estimate what we want to know, estimate what we can get from the sample data, estimator in an algorithm of how you go from data to get from the estimate. So how does it work? So obviously, when we measure just one parameter, then essentially all we have is the statistical parameters like averages and what's not. So what can we do? What can we do if we deal with more complex situations? So let's assume that we have our problem with the ice cream consumption. We have we have the accident rates. We have temperature. So let's assume that we don't have access to temperature. So we measure only. So let's assume that we want to find the true relationship between the ice cream consumption and the accidents. So does eating ice cream causes people to drown more often? We have access to statistics on ice cream, statistics for temperature, and statistics on accidents. But let's assume that we don't have access to the causal relationship. Can we learn the causal relationship between ice cream and accidents if we have access to the data? So it turns out that we can do that. So in this simple example, there is a thing called the adjustment formula. So the adjustment formula basically says that if we want to find out how does ice cream affect accidents, we need to calculate the formal formula. So we need to find out the conditional probability of accidents as the function of both temperature and ice cream, and multiply it by the probability of the specific temperature. So this is called the normal adjustment, and it basically tells you that if we have all our elements of our causal puzzle are observed, we would be able to discover the true causal relationship. That actually allows us to say, to formulate a policy. So if it turns out that ice cream, in fact, causes people to drown, then we should sell ice cream less. If it turns out that the relationship is obvious, is opposite, for example, people on the beach can choose whether they go, if they feel hot, whether they go and buy ice cream, whether they go to swim. So in this case, for this causal link, the relationship would be obvious. In fact, it can be that if we sell more ice cream, we actually reduce the probability of drowning because people are busy having ice cream rather than trying to go to swim to cool themselves. So basically, being able to run this estimate based on the data only allows us to formulate the policy of what we should do to reduce the number of accidents and make the right decision. So interesting thing is that the great thing about this type of framework is that very often we can make the right decision even if the true factor is not observed. So for example, this is the causal graph when A is affecting B and X, B is affecting Y, X affects Y, but let's assume that the A is not observable. So we somehow cannot see this factor. So what happens in this case, it turns out that we can still estimate the effect of X on Y directly. So if we change X, how it is going to affect Y, if we can observe B. Of course, the key thing here is that we need to know that the causal graph has exactly this form. So A can affect Y only through B and not either only through B or through X and no other way. But if based on our causal analysis or domain experience, we postulate that the graph goes this way, then we would be able to do that. And that's a big thing. So this is called adjustment criteria. So there is another example of how people can solve this type of problems, which is called front door criterion mediation. So let me illustrate the problem from which the example of the problem where the need for front door criteria appears. So imagine that we have a relationship. We have an observation that people who use the GPS more often have a less good memory. So I kind of have a feeling that that might be true because once the GPS appeared, I stopped trying to remember the roads. I just follow the GPS. And I think my memory for roads become much worse, but you never know. So the question is, what type of hypothesis can we make based on that? So the hypothesis number one is that the use of the GPS precludes memory development. Very natural. So we have a GPS, we no longer have to do it ourselves. There is a second hypothesis that there is a common unobserved factor that affects both the GPS usage and memory. So there is something that some inner factor that stimulates us to use GPS, but at the same time, it negatively affects the memory. So there are other examples for this type of things. For example, by now, we all know that smoking in the US is heavily discouraged, to put to the list. But several decades ago, there was a number of very big and very visible suits for whether essentially going to the point whether smoking causes lung cancer or not. And the arguments that has been made are exactly this type of hypothesis. So the people who started this suit basically said that the smoking causes lung cancer. And the tobacco company said that, you know what, there is a common genetic unobserved factor that makes people both more likely to smoke and facilitates the development of the lung cancer. The difference is obvious because if smoking causes cancer, then it is a clear case where we should smoke less. If there is a common factor that increases probability of smoking or motivation to smoke and causes the stimulate the lung cancer, that actually means that there is no relationship between the smoking and the lung cancer, and the companies are simply not liable for that. What can be done in those cases? So in these cases, this is called the mediating case, when we say that the influence of variable x on y is mediated by the third variable when there is at least one path from x, y goes through z. And of course, there is a fully mediated case when it only goes through z, and there are paths that go and that not go. It causes a partial mediation. And this is the example of how this approach of the mediation can be used to solve this relationship between the GPS and memory. So In this case, the authors of the study assumed that the capability of the human or generally mammal to orient in space depends on the volume of the hippocampus, which is the sort of specific region in the brain. So the assumption that can be made is that this volume of the hippocampus will fully mediate the relationship between the GPS usage and memory. So we assume that motivation can affect both the GPS use and memory. We don't know that. However, we assume that the hippocampus volume is related to memory, and the GPS will affect our hippocampal volume. So motivation is not observable, but the hippocampal volume is. That's something that can be measured directly using the brain scan, which basically means that if we have the observable, which is sitting on the causal path from we want to explore from GPS to memory, then we can come up with what is called the front door criteria. And that means that if we want to find out the effect of the GPS usage on memory, we need to calculate things based on this formula. So essentially, this is the probability of Z equal to certain conditional probability of Z on X multiplied by the conditional probability of Y on X and Z and probability of X. So this is fairly complicated. So kind of what does it even mean? It becomes much easier if we want to use the linear model. So if we assume that X and Z are linearly dependent and Z and Y are linearly dependent, then if we want to find the effect of X on Y, all we have to do is to fit Z on X. Then we have to fit Y as the function of Z and X. And then we need to multiply the coefficients from this model to this model. So this product will give us the effect of X on Y. So notice that, again, this becomes complicated, and it becomes heavily dependent on what causal network we, in some sense, either discover or postulate. But it also illustrates that these problems can be solved, and it can be a very useful exercise to find the equivalence for something like this in the manufacturing scenarios. So what do we do if we have more complex cases? So what I've shown you is the specific case of the chain and the specific case of the common observable latent factor. So can it be generalized? So yes, there is a thing called the do calculus that has been created by Judy Perel. So it's probably kind of close to impossible to figure out what it is going to mean, because kind of unpacking each of those relationships can take quite a while. So let's just not do that, because that's kind of the mathematical notation and all its beauty. But the important thing is that do calculus exists and it's complete, which basically means that all causal problems have a solution. So not so good news that it can kind of be quite incomprehensible and take quite a while to learn, especially to apply it for specific problems. Super good news is that by now there are codes like do-Y made jointly by Amazon and Microsoft that allows us to apply it. So that's a super good news, because for many things like Gaussian processes, the activation barrier is twofold. Actually threefold. One is to learn what it is on some level. Second, figure out how to apply it for our specific problems. And third, being able to implement it as a code. So generally, learning what it is something that you can do as a hobby, and kind of that's probably the reason why you are part of this seminar. Figuring out, so that's a kind of general knowledge. Figuring out how to apply it to your specific problem, it's always a challenge. So you need to be an expert in your problem and figure out how to apply these tools in the proper setting. That's something that is difficult, and doing it first time is a challenge. Notice that in computer science, most of the use cases by now are well established. So everybody understands what is chatbot, what is the recommender system, what is the autonomous drivers, and so on and so forth. So the use cases in CS are, or ad placement was not. Use cases in CS are established. So the primary work for all of us in applying these methods in material science is figuring out how to apply them. It's not straightforward, especially for something as complex as this one. But it is doable, and that requires essentially a single person to understand it once, and then we are good to go. The development of the code base that allows to implement this type of things is requires a community effort, and it's very expensive. So the good thing is that now the problem is reduced to the point that a single person can make a difference. So as long as we understand what goes on and how to connect it, we can apply in our everyday work, and the code bases are there. We just need to apply them properly. So finally, the last thing that I want to show, because it's kind of important and something that we encounter very, very often, is what is called the instrumental variable. So imagine that we want to estimate the effect of X on Y. So we know that both X and Y are affected by the common unobservable factor. So the question is, can we figure out the direct relationship, causal relationship between X and Y? The answer is not really, because this backdoor criterion, we cannot use it because Y is not observed. The front door criterion, the mediation, we cannot apply it because there is no mediator. So instrumental variable is a very special type of causal analysis where we introduce a special variable called an instrument, and the instrument has to satisfy the three conditions. So it should be associated only with X, but not with Y. It should not affect Y in any way other than through X, and there should be no common causes between Z and Y. So Z affects only X, there is no common cause that will affect Z and Y, and all the effect of Z on Y is through X. So this can be, essentially, this is what we call a context. So this is something that we know about our treatment, and sort of all additional information that's relevant to X but not relevant to Y. Turns out that in these cases we can actually use the causal discovery to find out the relationship between X and Y. This is the example of this instrumental factor analysis. So imagine that we want to figure out the relationship between how much time we spend education on the income. So in this case, the level of education can be affected by many factors, like family background, but family background also observes earning, right? So very often, if I'm coming from the kind of upper class family, that affects what type of school I'm going to go to, but it also will affect what type of position and industry I'm going to have. So if we simply try to find out this effect by doing the linear regression of earning on education, this can be biased by the things like family background. And we don't necessarily have access to family background. So nobody has it's not kind of clear when you look at the person whether this person comes from the family with the average income of 100K per year or 10 mil per year. So question becomes, can you find an instrument which is correlated to education but doesn't directly affect earnings except through education? And let's say that such instrument is proximity to college. So how it is done? Then in this case, it's kind of very simple. It's called the two-state least square regression. So you basically calculate the value of education as a function of proximity to college. You find out the effect of the outcome on the education, and then you basically get the estimated causal effect. So that allows you to isolate the variation in education from the unobserved confounder that also affects earning. Now, the difficult part here is that the key thing becomes how do you select the instrument? It's difficult. So for each area, the instrument selection becomes essentially a challenge. So it requires domain expertise to make them correctly. And if the instrument is chosen incorrectly, then you get the false relationship. That's why it's difficult. Now, this being said, we looked at three most simple cases. So we just introduced the concept of the causal graph. We illustrated the paradoxes that can happen, like Bjorkson or Simpson paradox, that happen if we don't understand the causal structure. Again, a very important thing is that always separate the science versus the policies. The role of the causal discovery is to understand what goes on, what is the causal structure. It is very different from the policies, meaning what type of actions are we going to take based on this mechanism. So it applies for everything. It applies for science, or cases. So what we discover is very different on how this knowledge is going to be incorporated in business practices. It, of course, applies for everything related to the social and economic issues. If we have the understanding of what goes on, it's still a very different story of what would the politicians do based on that. That being said, we looked at the three simple cases, which basically says that the causal discovery is a thing. There are a package solution for the simple cases that we can use, like front door criterion, back door criterion, and the instrumental variables. So what happens if we have more than two observables? Is it common? Absolutely. So the examples when the causal discovery can be super important is the biochemical reaction network. So I speculate, but I think that the causal exploration of what happens in the human body, the metabolic mechanisms, and correspondingly choosing the drug targets is probably something that the companies like AstraZeneca or Merck or large number of startups are working on, just because that's an obvious thing to do with a clear defined value proposition. Another example, anything related to the atmospheric reaction network. So the whole balance of the sort of human kind of climate and so on, and environmental impact depends on the reactions in the atmosphere. So this can be very complicated. Figuring out what is the cause and what is the effect is kind of important, because ultimately some people talk about using some form of the geoengineering in order to affect the climate changes. So in order to use it well, maybe a good idea to have a very good understanding of what is the causal mechanism of the environmental processes rather than just correlative. Otherwise, we can very easily encounter the situation of the Simpson paradox type, except that the opposite effect would be not terribly good. And so on and so forth. Like if we want to study catalysis, typically there are multiple sites and multiple reaction pathways, so we have the same type of problems. So this being said, and to close this segment, why causal experiment is difficult? It's difficult because essentially it brings the statistics to the real world, and we have to deal with the fact that there are a lot of common causes that we cannot measure. We have to deal with the measurement and discretization errors. We have to deal with the fact that the same sample can have multiple causal structures and we don't know how to separate them. We have to deal with the fact that the same behaviors can be explained by the number of models that feed the data well. Our search spaces are important, and so on and so forth. So causal inference is difficult. The problem is that if we can run the experiment, we should always run an experiment. Experiment is the ultimate answer to the causal problems. But not always we can run an experiment. That's why we need to do that. With this being said, and spending an hour talking about why the relationships between the variables can be complicated, let's go back and talk about how we can use the Gaussian processes in orchestrating the multiple experiments. So notice that when we talk about two experiments, our possible causal relationship would be relatively simple. But once we start to talk about more than two experiments, that in fact can become kind of complicated. And then we actually need to think about the causal issues. So for the time being, for the automated experiments, we discussed generally three types. So one type is the direct automated experiment, where we simply run the experiment the same way as the human would run it, means the fixed policy. And we just substitute the human analyzing data by the machine learning agent, like a deep convolutional network or something like that. So in this case, this is a fixed policy experiment. They just proceed. We just kind of change the human solving certain tasks by the ML agent. Another example is the myopic discovery experiments, like a Bayesian optimization. So in this case, we have the reward function. We plan ahead for one step. We can have human in the loop, as we discussed for the DKL, but generally this is a case when the reward function is available and we try to kind of run the loop to optimize it. A multi-step experiment is when we have multiple steps in the loop. In these cases, we need some plan for multiple steps ahead, but ultimately we also have some form of sparse reward function. So this is great, and the frameworks for those exist, but that's interestingly not enough for us to run the multimodal experiment. So as I said, the part of the difficulty for applying machine learning in the real world problems is because there are things which are elementary, but then humans are actually very good in solving complex problems, and machine learning frameworks that exist to help us solve these problems on the same level as human are still evolving. So for example, for this combinatorial library example, we have the problem of the making decision how to choose the right locations for measurement. So as I said, we can study it by electron microscopy, very expensive and time consuming. We can study it by Raman, very rapid. We can study it by the hysteresis loop measurement, sort of intermediate. So this takes fully automated, takes maybe a few hours. This takes maybe 2 days. This takes something like a week per sample. The question becomes, how can we use one method to accelerate the discovery by a different method? By now, you already know that the basic frameworks for that exist. It's a multitask and the multi-fidelity Gaussian processes, with or without structure. The difficulty is that we need to choose what we want to explore. Our methods don't give the information in the form of one reward function. They give us the information in the form of complex observation, like spectrum or loop or image, which basically means that if we want to run the experiments in some form of orchestrated way, we need to find parameters that we care about. And we can do it two ways. One way is to identify the physics-based scalarizer. So for example, we want to look at the we want to discover the areas where the hysteresis loops are largest. Another way to do that is to look at the predictive uncertainty. So in other words, in this case, we don't care what the loops are. We just care about what is the trend, how they change across the material system. And then we assume that the rapid changes in the behavior of the loops may be associated with the regions where there is something interesting happening that we want to understand with the high resolution imaging. So how can we do that? So one scenario is that when we first run the one type of experiment, and then we use the results of the one type of experiment to choose the location for the second time. So this is multi-fidelity or multitask when one is fully known. So this one we actually can do by now. The more complex one is if we want to orchestrate several observations. So for example, imagine that we have two halves of the same combinatorial library. One half is under the scanning probe microscopy system. Another half is in the micro-Raman system. And what we want to do is we want to make an SPM measurement, and based on the SPM measurement, we want to tell Raman system where to do the measurement. So the same thing can be SPM and X-ray, it can be non-indentation. So as long as we have the common object, we can run multiple measurements on the same object. Same problem can appear if our instrument has multiple observational modalities, which are mutually exclusive. So we run one measurement or another measurement. Same type of problems appear in the context when we, rather than having the two examples of the combinatorial library, we have the rapid synthesis system, for example, pipetting robot or microfluidic system, which essentially allow us to explore the same compositional spaces, but one of these microfluidic systems is connected to the synchrotron somewhere in argon, another is connected to the NMR, for example, in the UT Knoxville. So it doesn't have to be a combinatorial library, it can be a machine that produces samples fast. So how can we co-orchestrate exploration of the same space by different modalities? So this is just starting that we starting. This is just something that we just start to scratch the surface of, but it turns out that we can maybe not build solution, but hack a solution for this type of problems using the tools that we have already seen. So, for example, we can use autoencoder in order to simplify our data. So we have access to the data, which is high dimensional. Autoencoder makes it low dimensional. And then we have autoencoder that we can train on one source of data and get access to one set of latent variables. And we can have autoencoder that we train on the different set of variables. We have so it gives us a second set of latent variables. And then these are already low dimension. So then we can use the multitask Gaussian processes in order to choose whether we measure task 1, meaning one observation, or the task 2. So obviously, here the criterion is whether the latent distribution of the VAE is stable, because we assume that if we get new data and the meaning of the latent variable completely changes by inducing new data, it's not going to work very well. But the natural criteria here is that at some point, if we got enough data, latent variables stop change. And it turns out that this approach is actually working. So this is the example acquired on the dummy data sets. So meaning that they were pre-acquired on the grid. So what you're looking at is that you have a blue curve and you have the red curve. So there is a blue solid curve. So blue solid curve is the surrogate model. The blue zigzaggy curve, this is a ground truth data. So we did measurement on the grid both for blue curve, which was PFM, and red curve, which was the Raman. So once we have the model, we train it only on the small number of measured points. So we see 1, 2, 3, 4, 5. So at the edges, we measured both the Raman and PFM. In the locations in between, and two locations, we measured only Raman, and in one location, we measured the PFM. So there are 5 measurements of one functionality, there are 4 measurements of another functionality. So in order to see whether our algorithm works at all, we give it access to the ground truth data. But ground truth data is not a part of making decisions, it's something that we use for us as the human operator to see whether things work or not. So as before, the blue curve and the dotted blue curve are the ground truth behavior and the surrogate model. And you can see that initially the surrogate model is very different from the ground truth behavior, and it comes with a pretty high uncertainty, as we can expect. So the red curve is the same thing for the Raman. As you can see that the red curve is very different from the ground truth, and the uncertainties are very high. So see what happens. Oops. Somehow it was supposed to run as an animation. Let me see. Here we go. So see what happens if we simulate the active process. So if we run it, you can see how the ground truth behaviors are changing because our encodings are changing. So we update the autoencoder with the new data. But at some point, they stop changing, so it becomes stable. We got enough data for the VIE to converge. And while it's happening, our surrogate models have become very close to our ground truth models, which basically means that we have discovered the ground truth behavior. Look at how many measurements it has taken. So in this case, it's about 25 measurements. So we had 7 seed points. This is the fidelity trajectory. So this is our algorithm deciding to measure one parameter or the other parameter. And then you see that we were actually able to reconstruct the models reasonably well. So what did we learn? So the first thing that we learned is the decoding functions. So we measure spectra, and we measure the hysteresis loops. What we learned is the decoding functions that take the latent variables and allow us to reconstruct the spectra based on these latent variables. So in some sense, we learned what is the shape of the lock. So the second thing that we learned is the spatial distribution of the latent variable. So latent variable is, again, by definition, is the hidden factor that controls behavior of the system. And it sort of represents the physics of the system. And in this case, the latent variable actually looks very reasonable. In fact, this type of behavior tells us there is something interesting going on the morphotropic phase boundary, which is in some sense we know that it's interesting, but having the algorithm discover that there is something interesting in this location is actually very good. Correspondingly, Raman did not show us much for one very simple reason, that the Raman spectrum in the system is controlled by the substrate more than by anything else. So it's just a linear function. What's limitation of this analysis? So for limitation for this analysis is that we assumed that the kernel that relates the Raman signal and the PFM signal is symmetric, which basically means that their relationship is symmetric and correlative. In this case, this may be not so bad. But if we try to use the same type of approach in order to understand the more complex systems or processing optimization of what's not, we should not use symmetric correlation kernel blindly, because for real world problems, we need to take into account the causal structure between our control variables and observables. So again, the framework for doing it is not yet available, or let's put it this way, the framework is already available because there are things like do-why that allow you to do that. I'm not aware of the single case when it was done, but I'm reasonably certain that that's something that a lot of people are working on simply because it's important. So maybe these people are in startups rather than in academia, but it doesn't matter. So we also can get an idea about how successful the project process was based on the evolution of our interesting, it was supposed to start normally. Based on the evolution of our latent variables. So again, the red are the actual experiments, and the gray points is the ground truth data that we have access to in this case. But you can see that after a while they stabilize, which means that all the points, both the measured one and unmeasured ones, are sitting on the same manifold. So the concept actually worked. Now, the last thing that I want to show briefly is what else can we do? How can we bring the theory in the loop? So notice that theory in the loop and digital twins is one of the most spoken about concepts now. And everybody have a different meaning of what the digital twin is. So some people think that this is just a predictive model that is updated based on the experiment. Some people take it as the basically a compendium on data, which has enough correlative data that it allows us to predict the system behavior in the future. So depending on the field and depending on a relative balance of the data availability versus the modeling culture, everybody has slightly different idea about what digital twin is. So for us, the problem is that sometimes we have to deal with the expensive experiment and expensive theory. And the question is that if I want to run theory and experiment kind of in parallel, what type of decision making should I use in order to choose how to make theory and experiment kind of reinforce each other? So it turns out that this is actually a very, very complex problem. And it's very complex because most of the time when we use machine learning to solve the real world problems, we simply don't touch the problem of interaction between the theory and experiment. So for example, by now there is a tremendous amount of work when people use machine learning for prediction of the drug targets. And 99.9% of the time, the way that this is done is through the concept of essentially computational screening. You start with some computational space of molecules. It can be some standard data sets. It can be a generative space of the autoencoder. It can be simply the list of the molecules that you can commercially procure. So if you want to be practical. And then you start to apply the series of filters. So first you apply the cheap but not very predictive filters. Progressively, when your number of molecular candidates start to decrease, you start to apply more expensive but more kind of more high fidelity filters. And then you end up with several tens or several hundreds of the molecular candidates having the property that you're interested in. Then sometimes we evaluate their synthesizability scores. So very often qualified synthetic chemists can look at the molecular structure and say this would be easy to synthesize or this would be impossible to synthesize. And to some extent, we can use machine learning to do that. And then once we evaluate the synthesizability score, we can farm this out to the CRO like WuXi or Enamine or whatever. And then the molecule is being made, then the molecule is being tested. Synthesis takes months, very often takes months. Testing depends what you want to test, but if you test the drug, that takes years. If it is successful, if it fails, then nobody cares. But the point is that by the time testing is done, very often the people who did the theoretical screening do something totally different. So what we generally don't do is we don't have a feedback from theoretical prediction and experiment back to theory. So in other words, if we predicted certain property, then we synthesized it and measured this property, we generally don't get a feedback. And there is a very good reason for that, because the theory in this case is usually some form of the density functional theory. And of course, we are not going to change the DFT models based on the results of the single experiment. So if we want to talk about the theory in the loop, we clearly require a different use case where the theory, in fact, can be updated based on the experiment. Otherwise, if theory is immutable, then if the experimental prediction does match theory, that's the problem of the experiment. In real world, we run to, or in kind of in many cases, we run the experiment, we want to change the theory based on the experimental results. So what is necessary in order to make it possible? So the first thing is that we need to define the space over which theory and experiment actually operate. And when we talk about molecules, we generally have an idea that the molecule as represented by its formula and the molecule as it exists in the real world is roughly the same object. It's not exactly the case because there are a lot of factors like association, interaction with the solvent molecules and so on, but roughly it is the same object. Notice that solvents and so on, that's a part of the hidden latent variables that actually will matter if we run the causal analysis. Sometimes it's not the case. For example, single crystal of silicon in theoretical model and the real world silicon with the doping defects and microstructure is absolutely not the same thing. And the difference between the two depends on what characteristic we study. So from a point of view of X-ray, it is roughly the same thing. From the point of view of conductivity, obviously what we get from the band structure calculation for pure silicon and what we have with the silicon, which has a little bit of impurities, is obviously totally different. So the requirement for building theory in the loop requires that the objects are the same or made the same. The second part that matters is that the theory prediction and experimental prediction has to be compared one by one, which is also not necessarily given because theory predicts things of certain type, like optical spectra, band gaps, dielectric functions, what's not. Experiment often measures things which are related but not exactly the same. There can be epistemic uncertainty, or there can be a problem with the uncertainty related to the observational system. So our experiments are not ideal either. Therefore, we need to make sure that we trust both the fact that the object match and the observations match. Otherwise, we cannot even start. We effectively would be talking about apples and oranges. However, if this is the case, what is the next step we can do? And the answer is that we can actually sort of co-navigate the theory and experiment if we are running two active learning loops at the same time. And then, for example, we create the surrogate model for experiment, we create the surrogate model for the theory, and then we run the additional loop, which basically steers the prediction of the surrogate model for the theory so it matches with the experiment better. So this, of course, is a fairly complex scheme because we have one learning process, we have a second learning process. In this case, we say that we trust the experiment absolutely. We just want to update the theory based on the experiment. So we use a way to steer it. And interestingly enough, that this approach works. So I'm not going to go through the detail because this is highly specific to the system, and we had to choose the model that we have access to and the experiment that we have access to. But generally, model is something that is easy to compute. So this is just a combination of Ising and the Ginzburg-Landau model. The way we can represent the infrastructure, real material structure, is through the distribution of certain parameters, which basically fix the polarization. The important thing is that this model, despite its simplicity, can give the same variability of the observables as the experimental data set, which basically means that we can compare experimental results and the theory predictions essentially one-to-one. Then if we combine these elements together, it's actually possible to make it work. So for example, for the theory comparison, you can see how the theoretical experimental model trains. So this is the learning of the experimental loop. This is the learning of the theoretical loop. So it's much more erratic because we update theory during the process. So it turns out that at least we can get the comparison, we can get the prediction close to the ground truth. So that's already kind of good. It turns out that much like for this ferrocene model, there is a reason why it is not straightforward. So it turns out that the real world problem, if you explore them, the ground truths, they very often have the very, very complex behaviors, which are actually ill-suited for the Bayesian methods. I mean, they're even worse for the gradient descent. Bayesian at least works. But anyway, that's possible. Now, let me finish with making some general comments that where are we going with that? So both in the experiment and the characterization, the current paradigm is very separated activities. So for example, in microscopy, the paradigm is that there is a single scientist who works on the instrument. So it is multiple hours of full day sessions. The results are analyzed by the single scientist. They are communicated to the community through the preprints or conferences or papers. So usually that takes weeks or months or years, actually. So this is changing. So one thing that is changing now is that we can at least technically connect multiple instruments into the integrated network and have the multiple human scientists interact with them at the same time. So in microscopy, it hasn't happened yet because it's not clear what is the downstream benefit. In areas like high energy physics or astronomy, it is basically the reality. Now all the big facilities operate in this type of cloud integration scheme. Another important thing is the fact that we're starting to have the automated expert system that help human to analyze the data. So, I mean, with the ChatGPT that already happened, very often you can start with the prompt to effectively go from the prompt kind of dialogue with the ChatGPT to the point of ChatGPT creating the code that can you make a part of your experiment to analyze the data as it streams. So this process can be automated more, so something that people call a co-scientist, but practically it's already doable with the classical OpenAI interfaces. The part that is a big challenge, in my opinion now, is the transition from these tools to actually workflow design. Because as I showed in the very beginning, the whole process of the scientific discovery very heavily relies on the prior knowledge and curiosity and anticipated value. And generally the designing the way how we synthesize and characterize materials in order to get some specific objective is actually very, very difficult. And it requires a lot of building blocks, which are not necessarily known or available. So Bayesian optimization is just a starting point. And then simply involves some groundwork and like reward values policies and so on that are simply not a part of the classical material science curriculum. So I hope that this set of lectures both illustrated what these concepts are, gave some tools that allow to use them at least for the simple scenarios, and most importantly, kind of gave some idea about what are the things to keep an eye open for as the causality which can kind of affect our decision making. Why does it become important? It becomes important because fully automated execution of the workflows is no longer an abstract concept. So there are places like Emerald Cloud Lab, with one example in Carnegie Mellon, another moved from San Francisco to Texas recently. But basically, you can have an access to the all equipment for, let's say, organic synthesis and so on in the same place. But you need to provide the workflow that will tell this equipment what to do. And that, of course, is a challenge. That's why we had this course. So what does it take from more general perspective? So we talked a lot about the specific methods, but what's the big picture? And if we want to have the design of the workflows, we of course need to have the labs to do that. These labs already exist. It doesn't require the cloud lab. It can be the lab that you now work with. We need to have the workflow design. So humans understand manuals and instructions. AI understand can learn by themselves. AI understand only codes, which basically means that we need to create the hyperlanguage that allow us to connect our commands to the AI execution. That is being done now, and by now realized by quite a lot of instrument manufacturers. So that's being done. If not, it's relatively straightforward. We just enumerate what the humans can do. But then it becomes complicated. So we need to define the domain-specific reward functions. How can we judge the success of experiment? If we can do that, then most of our problems become optimization problems. If we cannot do that, then machine learning is simply not something that we can use. We need to learn how to integrate the reward functions from dissimilar domains. So how does beta microscope help us learn physics better? Or why would specific DFT calculation help us understand experimental data? This is super difficult. So for some cases, it is possible to do that, but it requires digging very deeply to the basics of the method. sometimes it's complicated because we talk about the general decision-making capability, which is something that humans are good at, if not necessarily introspective, and machine learning simply cannot do that. We need to learn how to make hypotheses. So that's also difficult. Humans can do that. ML, I have big doubts. And I kind of, for the time being, I think that this is going to be remain human activity for a long term. Then, of course, we have hypothesis generation beyond human level, but that's a kind of question of the artificial general intelligence, and sort of it's a little bit more theology rather than science. But the important thing is that it's definitely the case that techniques like Gaussian processes, structured GPS, multi-fidelity GPS, they allow us to connect multiple humans and multiple labs into the same code. It's complicated because beyond elementary methods, we start to have a lot of parameters that needs to be controlled and balanced by human, but that's what makes it useful and interesting. And final thing that I want to mention is that imagine what will happen. It was actually very funny. So I've been on the NSF workshop in winter when one of the tasks for the panel was try to predict how the automated experiment is going to look in 20 years. And this is a very tall order simply because automated experiment as a field exists for the last 5 years at most. There were people doing it before, but as the field, meaning multiple labs connected to each other, exchanging experience and so on, and being perceived as something solid by the scientific community, it's a very new field. And a lot of things that we are doing now, 5 years ago, would be sci-fi. So trying to predict what's going to happen in 20 years is obviously difficult. But if you think about it, ultimately we are going to the point that there are some things that humans can do and some things that AI can do. These things are complementary. And then we start to say that humans, we are going to have the collaborative environment where humans and AI interact. We realize that we have some specialization. Some of us are experts in material synthesis, some of us are experts in microscopy, some of us are experts in theory. All of us have different objectives. So some of us want to make materials to solve global warming, others want to make materials for better batteries. We all learn, we need to make real-world decisions, we need to be in the interactive world, we need to manage resources because obviously experiment comes with the price. We need to kind of track our progress. And then if you put all these elements together, then it almost looks like that the future of the automated experiment would be like a giant computer game, because that's exactly where human agents interact with the multiple AI agents, and that's simply how the game like World of the Warcraft works. And the interesting thing is that I thought that I'm going too far with that. And it turns out that out of the 4 people on the panel, all 4 came to exactly the same conclusion, a slightly different form. So I said that it's going to be more like a MORPG. Some people said that it would be more like a computer games like Scratch, where we also have a gamified interface. But ultimately, that's actually what's happening. And interestingly enough, in Seattle, in University of Washington, there are already centers that combine biological research and the gamified system. So this is the future that is actually happening as we look at it. So for the time being, we just learned how to run an optimization on one very small loop. So to finish, when you do science, there is a kind of very popular viewpoint that science is delivered by new ideas. But the statement that resonates with me much stronger is that by Freeman Dyson, who said that new directions in science are launched by tools much more often than concepts. And the effect of concept-driven revolution is to explain all things in new ways, like quantum theory. But the effect of the tool-driven revolution is to discover new things that have to be explained. And that tool-driven revolutions are much more common. So I think that we are now at the point when these new machine learning tools are added to our domain, and they're going to make all the difference in the world. So I would like to stop. All the notebooks for this course are on the GitHub, and I would be delighted to stay in touch and answer your questions. Thank you. So any questions? Okay, if not, then thank you very much for attending. Please feel free to contact me if you have additional questions or would like to learn more. And it was a pleasure, and I hope it is useful. Bye.
Thank you, Sergey.